What's going on, guys? If you're watching this, I hope you had a good Christmas. In the last couple videos, we've been working on a pathing algorithm for our enemies, and the pathing algorithm that we made was pretty good, but it had a few major problems. So the way that it worked is that the enemy would cast a ray towards the player, but the ray would only go a short distance. It wouldn't go all the way to the player. It would only go 5 at a time. And what would happen is it would keep casting it. So every time it casted a ray, if it didn't hit anything, it would add distance to a list of waypoints for the enemy to go to. And then eventually, if it hit an obstacle, the way that it would handle the obstacle is it would go 5 degrees to the left, and then 5 degrees to the right, then 10 degrees to the left, then 10 degrees to the right. And then eventually it would find a path around the obstacle, and it would eventually find a path to the player. And this is why this didn't work. So consider this situation where you have an enemy on the right side of an obstacle that's at the top or an edge of the room. Well, if the enemy tries to cast a ray at the player, he'll eventually find this position to go around the obstacle that's closer to the edge of this square. But the problem is when you cast a ray from the enemy towards the player after you've moved down, the next point that will get drawn is always upwards, so the enemy will get stuck going back and forth forever. And this isn't actually the behavior that we want. So then to get around this problem, I tried to use the dot product. And you could take the two vectors and you can calculate how close they are together, like angle-wise. If it's close to 1, that means that the angles are close together. And if it's close to 0, it means the angles are far apart. And I use this to try to make sure that each point that gets drawn can only be within a certain angle. So if a dot gets drawn and we go to draw another dot, it can't be 180 degrees in the opposite direction. And this would eventually prevent the enemy from going back and forth. But then we ran into this problem where if the player ran directly past the enemy, he would end up having to go in a gigantic circle to avoid going over the angle threshold that we set. So I ended up scrapping the dot product algorithm because it wasn't really behaving the way that I wanted it to. And this is the last thing that I came up with. So my new algorithm took all of the obstacles in the room and calculated a point close to all 4 of the corners of each obstacle. My enemy would then follow the original thing he was doing, but when he ran into an obstacle, instead of doing the 5-degree left and right thing, he would pick the closest corner that he could fit in, and he would use the corners of the object to go around it. So as you may have guessed, this didn't work, and there's lots of shape like this one, where if you get the corners using the height and the width, your character will end up walking around it as if it's a square, but it's not really a square. Obviously, it should be going inwards. Now, you could get around this by raycasting from the corner towards the middle, and you could get the hit point, but there's also lots of cases where that might not work, like if there's holes in the mesh or anything like that. At this point, I decided I was wasting too much time creating my own algorithm, and I was just going to use one of the ones that's already tested and known to be working. And this is when I discovered this 10-part series by Sebastian Legoux, and I hope I'm saying that right. And this series was really, really well done. So if you're trying to learn the exact details of how the algorithm I'm going to explain to you works, I would definitely recommend following his series. He implements it in such a great way. But I'm just going to be summarizing all the videos for you because I followed all the videos. And you can actually download my resulting code from the description of this video. And that's what I'm using in my game now for my enemies. And I'm going to be showing you how to implement it after I'm done explaining the algorithm. So in the first video, he just kind of explains how it works. Now his explanation is probably a lot better than mine, so I would definitely recommend watching at least the first video in his series so he can thoroughly explain how it's working. But I'm just going to basically mansplain it for you. But this is point A and this is point B, right? So you have point A is where you are and point B is where you're trying to get to. So the algorithm will draw a huge grid on your game. Each square that's around, hang on, let me make it black. Each square that's around your character or your position, right? And it calculates the F cost and the H cost. So if you go left, like a straight direction, the cost is 10. And if you go diagonal, the cost is 14. This is because it's the square root of 2. Again, he explains this really well. This is just a quick explanation, okay? Then the other cost, I think, so this is the F cost and this is the H cost. The other cost is the distance from the target, right? So because this is diagonal, this is 14. This is 28, this would be 42, and then this is 56, right? Because you're just adding 14 because it's diagonally. If it wasn't diagonal, let's say it was here, it would be 10 down and then diagonal, right? So the closest distance to it. So that's how the algorithm is working. So then you take both of these and add the number together to get the final cost, and then it just gets all the nodes around it, and then it sees which one is the lowest of all of these numbers. And since the 42 is the lowest in this case, it will get all the nodes around this one. Because it found the target, it will go backwards and find all the lowest costs, and that's how it finds the path. So that's a very, very quick explanation. Again, he does a way better job explaining it, but that's what the first video is. He's just explaining how the algorithm is working. So in the second video, we basically draw this grid on the game, right? So basically we take the size of the grid that we want, which in my case, in my main game is like 400 by 400, but in the other game, it's a little bit smaller. I think it's 100 by 100. And we make a grid on the game, and then we could actually get the position of any object in your game using this method that gets a node from a world point, and then we're drawing it using gizmos. So we're drawing a bunch of squares using the onDraw gizmos function inside of the game. Now, this is the script that's from the finalized version. In the version that he does in his videos, it's a lot simpler at this point. It doesn't have all this extra stuff in it. So don't try to copy paste this code. It's not going to work. If you do want to use this script or whatever, you can download the final result that's in the description of the video. So in the third video, he basically just gets the path. So he uses the formula that he showed us in the introduction, and he gets just the path. Now, this doesn't actually make the unit move or do anything. It's just the basic path from one unit to the other unit using the grid. In the fourth video, he shows us how to use a heap as a container structure instead of like an array or any other type of like list or other type of container. This is significantly more performant than the original way that he shows it in the other video. In the fifth video, he actually creates a script to attach to a game object to make a game object follow the path. So then videos 6, 7, 8, and 9 are all about path smoothing. So instead of the character just going, or the enemy just going directly to the player, there's a lot of factors in how he gets to the player. So let me run this and I'll show you. So that gray slab that you saw in the middle, think of this as like a road, right? So I've got two layers here on the right. We've got a movement penalty layer and the floor. Now the floor penalty is set to 15. So the regular floor, which is this gray normal area, is set to 15. And this movement penalty terrain, if I can click on it, is set to 0, right? So that means that the enemy should prefer to move down this road. Now, if you look at the road, it's not just all the same color either. So the edges of this road are smooth. So the middle part of it has the lowest penalty and the edges have the highest penalty. So what this will do is he'll go to the very center of the road to go down it instead of going just like to the edge and going down the edge of it. So let's hit play and see what happens. So you can't see my character because he has my enemy because he has a skin on him that thing is showing over top of it. It's using a shader and the shader is not visible over top of it. Let me just put a normal thing on him. Hang on. Okay, so now you can see him. And his speed is set to really low, by the way, because I didn't want him to immediately crash into my player. You can see that his path that he chose was in the middle of the road instead of going directly to the player because the penalty of the floor is set to 15, which is really, really high. And the movement penalty for this road that we've made is 0. So the penalty for this road is 0. And then this is nothing. There's a 15 movement penalty for the regular ground. So he'll always prefer to walk on the road. And if you look at the road, the middle of it has the lowest penalty and the edges of it have a higher penalty and it's blurred. So it's not just like all of it's the same penalty. And also all of these obstacles, you can see this little black shading around them. And that's because there's a penalty around the obstacles. So when he tries to walk around something, he'll actually walk. He won't just like drag against the wall. He'll actually go all the way around it and he'll actually try to prefer. He can still do it. Like he can still go directly next to an obstacle. Like if these two obstacles were like this, he could still technically go through it, but he'll prefer to go a little bit away from the edge of the obstacles. You could also do this the opposite direction as well. So instead of having the floor as having a high penalty, you could have the movement penalty. I have created a layer called the movement penalty. So like, let's say you have sludge on the ground or some type of water or something that's slowing down your enemy or your player, whatever's being moved by this, right? You could make it so that the movement penalty is higher and then he'll avoid this at all costs. So it's also worth mentioning that the blurring algorithm that's being used, if you have a higher penalty on this, for example, the penalty of this road is now, or it's not a road, it's just an object, right? It's 15. So because there's a higher penalty than the floor, the middle of it is where the enemy will avoid now. So if he has to go on this road, and we'll just call it sludge or something else right now. If he has to go in the sludge, he'll go only towards the edges of it, and he'll try to avoid the middle of it. So the way that the blurring algorithm works, it's based on the penalty. So if the penalty is lower than the other areas, then the middle will become more feasible. But then if it's higher than the other areas, then the middle will become the part that he tries to avoid the most. Hopefully the picture helps with like the representation of that. So, and you can see as he's following him around, he'll avoid, like he'll go all the way around the road, but he can still go through the road if it makes sense. So like the penalty is only 15. So like if he has to, he's not going to go all the way around the road to get to it. But if he can avoid it, he will. Like you see that he's going like this way. If I go like directly here, he'll go around it if he can. But if it's like in order to go all the way around the road, he would have to go all the way up here. He does a calculation to see if it's worth it instead of, like, it's based on the penalty. You could make this penalty massively high and then he would avoid it at all costs. Or you could make it lower so that he'll only slightly avoid it if it can be less or more, right? And then the last video is probably the most complicated of all the videos. So when your unit starts, which is like when he actually gets enabled in the scene, he starts this coroutine called update path. And then update path calls this other method called request path, which starts a thread which uses the instance of the pathfinding class to call a method called find path. And then this is the find path method, and it has a callback of a path result, which returns the waypoints with the request method callback. And then when the path is found, it uses the waypoints that get generated from the method to call a coroutine, which it stops the coroutine at the same time it's starting it. If you get a new path, you stop following the old path and you're just using the new path now. And then this is the follow path method that it uses, which eventually calls the follow path action. And the follow path action is where your character actually moves towards the final result. And this is where my code actually comes in, right? So you can see that I've made this method virtual. This is not actually virtual in the tutorial series. And the reason I've made it virtual is because the script that I attached to my slime that we're watching in this video is the slime script. It's not the unit script, but the slime script inherits from unit script. So when you create a new script and you say that the slime script is inheriting from unit, that means that this is the unit script. So by default, this is the same, like it has all of the same methods and variables as the unit script, right? And so by using a virtual method, what virtual essentially means is that if I don't declare this method in the slime script class, then it will automatically do this one, right? But if I do declare it, when this happens, it will be this method instead. So in my slime script class, I can call override and then this method name. And what this means is that I can have all of my units doing different things without having to actually rewrite all of the code. So instead of having a bunch of unit classes that have all of this garbage in it, we can create a slime method or whatever type of unit it is, and we can make them override the path action. So when the path gets updated, it can do different things. So you can see that my slime, he's growing and shrinking over size, and he's moving faster and slower while he's going towards the destination. And I'm going to go into the details of how the slime is working. Okay, so before I go over how the slime is working, and this is also going to be included in the description of the video for free. You can download the slime too, and you're welcome to use it in your game if you want to. I don't really care, right? So the first thing you have to do is you need to create a folder or a game object in your game. So if you right click on the left here, you can create an empty game object. And I've called mine A-star, but you can call yours whatever you want to. This is what will generate the grid, right? It has to be at 0, 0, 0. And then we're going to attach. So this entire folder, A-star algorithm, is part of what will be, if you double click on the package file that's in the description of the video, this will get inserted into your project automatically. And we're going to drag this grid script onto this A-star game object that we just made, as well as the pathfinding script and the path request manager. Inside of the grid script, your grid world size needs to match your actual floor, right? So like my floor is 10 by 10 and planes are actually 10 in size. So it's 100 by 100. So my A-star grid is 100 by 100. The node radius is how big each of your nodes is. So if I make this like 5, for example, it's a lot faster to have less nodes, obviously, but if the nodes are bigger, the path finding is going to be worse because like it won't be able to go as close to the objects and it won't have as much to work with. So let's turn this back off and put it back to 0.5. The lower the number is, the more little squares will appear. You can turn off displaying the grid gizmos if you don't want to see them. If you have a high number of gizmos, it will make your game lag depending on how good your computer is, right? So like you can turn them on and off. Obviously drawing like 10,000 squares or however many squares this is obviously going to make your computer go a little bit slower. So you obviously don't need to draw this. But yeah, after you've done that, if you run the game, it should automatically draw the grid in your scene as long as you've done it correctly. You need to create a character. So if you just drag in the enemy that I've added, so there's Circle Man 2, which is a prefab. Let me just see if I can find him. Hang on. Oh, he's not a prefab. I'm going to make him a prefab. Let me just do that right now. So hang on. So I drag him into the enemy folder. So I've already added the slime script, which is also going to be attached to the video, but all of this stuff will get imported. It's all going to be part of the same package. So if you drag Circle Man 2 into your game somewhere, it doesn't matter where, he should already have the slime script attached to him, and he should have all of like the stuff, like the settings that you need. And yeah, if you do that and you drag in target, so you see there's like a target. I have the Stick Wizard tutorial as the target. If you're not following my game, you're going to have your own target. So you need to drag a transform into the target slot and make sure all these fields are filled out. And then if you run the game, the enemy should be chasing your player around. So now I'm quickly going to go through the slime script and just kind of go over how it's working. So firstly, you have all the variables at the top that it's pretty obvious what these control. So time counter is not something you can edit. The oscillation speed is how fast so he's shrinking and growing, right? So over time he's shrinking and growing. He's also going faster, and then when he's smaller he's going slower, and then when he's bigger he's going faster, and when he's smaller he's going slower, etc., right? Because he's kind of like a slime. Eventually he's not going to be following the player around, okay? He's just going to be going to a random spot in the room. Picture like 5 or 10 of these in the room, and they just pick a random spot and they go they like get a burst of speed and go towards that spot, and then they slow down for a second and then they get a burst. This is how worms work in like The Binding of Isaac, if you've ever played The Binding of Isaac. Anyway, so the minimum speed is like the minimum of how fast he can go. You could set this to 0 if you want to make him not move at all, and then the max speed is like how fast he'll go when he's going the maximum speed, the min scale, the max scale. This is all obvious stuff. So you can fill out the variables. We're overriding the follow path action, which is happening every 0.3 seconds in the, so after 0.3 seconds of the scene loading, this is just happening over and over and over again every time there's a path that is received. Basically, the first thing it does is it rotates the player towards the first point in the path that leads to the player. So your enemy will turn towards the first point in the path that's leading to the player that you're trying to kill. The sign value, so here's sign, right? So sign is a number between -1 and +1. So this is time. So time 0, 1, 2, 3. So time is always counting upward. So it's always going +1. So 0 is actually -1, right? 1 is 0. 2 is +1. 3 is 0. 4 is -1, etc., right? So you get like this oscillation kind of thing where it goes up and down and up and down indefinitely forever. This is really useful for something like this where our character is shrinking and growing. So when it's 0, when it's -1, he'll be the smallest size possible. And then when it's 1, he'll be a medium size. And when it's +1, he'll be the full size. This makes it really easy for him to grow and shrink, as well as for the speed to, because the speed could also be controlled by this. If it's +1, he'll be going faster. And if it's -1, he'll be going slower. So we're taking the time counter, which is just a frame, and we're multiplying it by the oscillation speed. So this is how fast he'll start going slower and faster. So the current speed is going to be lerp, which takes these two numbers and it actually, so let me just get a new diagram going here. Hang on. So instead of it going from -1 to +1, we're going to be lerping between the minimum speed and the maximum speed. So you see up here, we've set the minimum speed to 20. And the maximum speed is 500. So instead of going from -1 to 1, it will be going from 20 to 500 to 20 to 500. So that's what lerp is doing here. And then this is the sign value +1, because we don't ever want this number to be negative. We only want it to be positive, right? So lerp is a number between 0 and 1. So instead of it being between -1 and 1, for lerp's inputs, we need 0 to 1. So we take the sign value which is a number between -1 and 1, and we plus 1, which means that the lowest value number is 1, and we're dividing it by 2, so the maximum could be 1. I hope that makes sense. It's kind of confusing, but just know that this is going between, this current speed variable is going between 20 and 500, and it's going like up and down forever. So we're setting the speed to be this number between 20 and 500, and then we're setting the scale, we're using lerp again, between the min scale and the max scale using the same formula, and then we're setting the scale to be the number, but we also only, so let me just do another picture because this is also kind of confusing. We have this blob person, right? And these are his eyes. So when you scale him, it's looking for 3 values, right? It's looking for the X, the Y, and the Z. So we're clamping his scale on the x-axis between, because we're not going to be changing the y-axis, so he's not going to be growing vertically. He's only going to be growing horizontally and towards you. So imagine like this is like actually towards the camera, right? So he's only growing the most in the x-axis. Sorry, in the most in the z-axis, so like towards where he's going, like in the direction he's going the most in this way. And then this is actually the x-axis. He grows a little bit in the x-axis. We're clamping the scale to be between the minimum scale, which is 1.5, and the minimum scale plus 0.5. So when he's the biggest, his x-axis will have only grown 0.5. So he'll be like only 0.5 wider this way. So he'll only be growing 0.5 outwards, but his z-axis will be going the full scale. So however, like the max scale is 2.5 in this case, so he'll be growing 2.5 like this. So because he's kind of growing like a worm, right? That's the whole point. So that's what the clamp is, just making it so that it's going only between the minimum scale, which is 1.5, minimum scale plus 0.5, so 2 in this case. But if we made our minimum scale bigger, it could be more. And then we're setting his velocity to be his forward, because remember, he's looking at the first point times the delta time, which is the time since the last frame, times the current speed, which is getting changed over time, like it's a ratio, and then times 200, because this is really slow, and I didn't want to have to add 100 values into, like, if you look at my settings inside of my circle man down here, my speed is only between 1 and 15. I didn't want to have to type in like 100 and 150 or like some huge numbers here. I just want to work with small numbers down here, so I needed to multiply by 200 in my code so that I could work with small numbers. And then down here at the bottom, if I collide with my player, then I add an impact. This just pushes my character backwards. And then this hard script take damage, we did a whole video on that, but basically it makes my screen flash and I lose hearts. So let me just show you this in action. Hang on, let me click play here. Okay, so he's going really slow. Let's just change the max speed to like 40. So like his max speed is a little bit faster. And you can see he gets like a burst of speed. Let me turn off the gizmos. So this is what it would look like when you're actually playing. You won't actually see like the grid or like any of those lines or anything like that. Oh, by the way, I didn't cover the turn distance. So even without weights or whatever, like the thing blocking the object, there, see how there's like a line? Let me just pause this. There's these lines. He will go in the average of this line, like in the middle. So like if he's trying to turn a corner, there has to be enough distance for him to fit, and he'll go in the middle. So like instead of him going like close to the wall, he has to be like this distance away from the wall. So like half of this away from the wall. Yeah, so this is what happens when he hits me. It's supposed to push me back, but I haven't really set that up very good right yet. The code to push it back is from my other game, and it's pushing back my Stickman Wizard, but this character is named Stickman Container, so it's not the same thing at all. So that's pretty much going to be it for the day. I hope you guys enjoyed the video. If you did, make sure you like the video and subscribe to the channel. And if you're using this algorithm, like if you're downloading it, make sure you go and like Sebastian Legs or Legoo's channel, because he's the one who actually, he didn't make the algorithm, but he's the one who did the implementation of it. And without his videos, obviously I would have had to implement it myself. So if you do like that, make sure you go like his videos and follow his channel or whatever. And yeah, hopefully I'll see you guys in the next one.